Hello everyone, I'm Sariaraki. I'm going to talk about modeling of DC motor and PID controller design. DC motor, a direct current motor, is the electric motor that creates torque by using electricity and a magnetic field. The input of a DC motor is current, voltage, and its output is torque. The compound motors are used where higher starting torque and very constant speed is required, such as grinders, lifts, and industrial equipment, such as fans and compressors. There are two types of DC motor. Brush DC electric motor. It generates torque directly from DC power supplies to the motor by using internal commutation stationary magnets and rotating electrical magnets. Brushless DC motors. It uses a rotating permanent magnet or soft magnetic core in a rotor and stationary electrical magnets on the motor housing. Operation of DC motor. Whenever a current-carrying conductor is placed in a magnetic field, it experiments a mechanical force. The direction of the current can be determined by Fleming's right-hand law. When armature windings are connected to a DC supply, current sets up in the winding and magnetic field provided by field windings. Magnitude is given by F equal VIL, where V equal magnetic flux density, I equal current, L equal length of conductor within the magnet field. Current carrying armature conductors experiments force due to the magnetic field. Commutator is made segmented to achieve unidirectional torque. Otherwise, the direction force would have reversed every time when the direction of movement of conductor is reversed the magnetic field. Advantages for DC motor are provide precisely speed control for acceleration and deceleration, simple design, high starting torque, and accurate steep-less speed with constant torque. Disadvantages for DC motor are high initial cost, cannot operate in explosive and hazardous situations due to sparkling of card brush, and high maintenance. Modeling of DC motor. A DC motor's speed and torque can both be controlled by varying the applied voltage according to the equation below. There are other ways to control the speed of the motor, such as pulse width modulation, but for our purpose, voltage control is sufficient. The block diagram for transfer function of DC motor and the equations of transfer function for DC motor. For a typical motor, this can be assumed to be J equal 0.01, B equal 0.1, K equal 0.01, R equal 1, L equal 0.5. Now I'm going to talk about PID controller, a proportional integral derivative controller. PID controller is a control loop feedback mechanism, and it is most widely used in industrial plants because of their simplicity and robustness. the effect of the PID parameter on the closed-loop dynamics and demonstrate how PID controller can improve the system performance can be shown by using MATLAB and Simulink. This is a block diagram of PID controller. And this is a block diagram on PID operation. The transfer function in the time domain and in the Laplace domain with Kp, Ki, and Kd and L is t. Kp is the proportional gain, Ki is integral gain, and Kd is derivative gain. PID controller result. By varying the amplitudes of the different responses for our PID, we can create a controller with the lowest overshoot and the best response time. For this particular system, the PID was tuned to have a rise time of 0.461 seconds, a settling time of 1.61 seconds, and overshoot of 6.4%. This is with a Kp of 90.46, Ki of 52.9448, and Kd of 1.5701. And it is the graph for tuned characteristic of our PID. Differences. Thank you for watching, and I'm sorry for my poor English.